Great. Thanks very much, everybody. And as advertised, I want to talk about the physics of flight. It's particularly a pleasure to be here at Trondheim since you guys have been using my physics book, University of Physics, for many years now, through many editions. And I'm happy to say that we're actually so delighted that it's used here at Trondheim that the latest edition has Norwegian content right on the cover. You'll actually see the Leonardo Bridge right here is actually prominently displayed, so everyone will know in the world that physics and Norway go together perfectly. Nothing that goes together perfectly, actually, with physics is flying. And that's something that's really close to where I work. Here's the University of California, Santa Barbara. As you can see, the skiing is nowhere near as good as it is at Trondheim. Surfing, however, is substantially better. And in fact, there are some student residences that are literally across the street from the beach. And so you can see why occasionally, in fact, very frequently, we get students from NTNU who will come to Santa Barbara for a year and change sports. And so if that's something you're thinking about doing, by the way, we encourage you to come to Santa Barbara. So the university is right there, but of course, right next to that is the Santa Barbara Airport. And so it's incredibly convenient for flying in and out of Santa Barbara. It's also incredibly convenient if you're a pilot. And actually, I am a pilot. That's actually me at the controls here. That's our airplane. And so I've got lots of practical experience. Been a pilot for over 30 years, flying all over North America, and also in Africa more recently. But one thing I found is that one thing that many pilots are confused about is what are the basic physics of what makes an airplane fly. And that's much I want to talk about today. One thing I find in all my teaching of physics is that even if you've never taken a physics class before, you're an expert in physics. You're guaranteed to be an expert in physics because if you come to the university, as I say, even if you never took any physics before coming to university, you have 18 years of practice doing physics because you've been running, jumping, skiing, turning switches on and off, catching baseballs and things like that, and you put together in your head a common sense picture of the physical universe. And the problem is it's completely wrong. And that's part of the reason why learning introductory physics is so hard, because you have all these incorrect ideas in your head. That's why in our textbook, we have lots of statements about so-called caution paragraphs alerting you to common misconceptions. We're going to try to actually see what some of those common misconceptions are today associated with flying. And we'll introduce some new ideas for you as well. It turns out that much of the physics of flight is really the physics of wings. The wings that you find on an airplane, that's the structure you will not find on other types of vehicles. You don't find them on cars. You don't find them on buses. And it's really the wings that make a difference. And it's not just flying machines built by humans, it's also flying machines we find in nature. So actually, as we go through the talk today, we'll see lots of connections between the physics of airplanes and also the physics of birds, because much of those are actually related to each other. There are some structures that you'll find on modern airliners, for instance, that are directly stolen from structures that you find on birds. So we'll see what some of those are like as we go through today's talk. So we're going to talk a little bit about what it is that makes an airplane fly. There's lots of misconceptions associated with that. We'll introduce the idea of lift, the force that actually, for the kind of flying we're talking about, acts vertically against the force of gravity. We'll talk about drag, which we'll find is more than just air resistance. There's an important part of drag that's actually, unlike air resistance, which gets more important the faster you go, there's an important type of drag that gets more important the slower you go. And we'll talk a little bit about why different wings are shaped in different fashions for different purposes. So let's begin actually with the question of what is it that makes an airplane fly? So that's an excellent question. I know we have some really expert physicists here in the audience. So for instance, our friends here from Oslo, you can tell me what is it that makes an airplane fly? Not to put any pressure on you, of course.
It's the force that pushes it up.
Well, that's part of it. That's part of it. Well, let's see. Some of the locals, what do you think it is that makes an airplane fly?
Airflow or the wings.
Well, again, that's part of it. Let's see. Are there any pilots here? Because I guarantee if there were pilots here, they would know the answer. Particularly if you're a private pilot and you fly yourself, you know the one thing that actually makes an airplane fly is money. The statement goes, if God had meant man to fly, he would have given him more money. And it's also said, I know there's money in aviation because that's where all of mine went. So whether you're playing in krona or playing in dollars, it is an expensive thing to do. But the question is, once you have that money, how do you properly arrange the airplane so it can actually leave the ground. So, and it'll turn out that, in fact, much of what you were saying is exactly correct. It really has a lot to do with the manner in which air flows around the airplane, and the wings are an essential part of that. For the kind of flying we're going to talk about in this lecture, while some of the most fun stuff to watch is aerobatic flying, doing all kinds of amazing maneuvers, it turns out if you're actually in aviation, it turns out that flying straight and level, constant altitude, constant speed, that pays better. The airline pilots actually make much more money than the aerobatic pilots do. So with a mind to practicality, let's actually talk about the better paying kind of flying, and let's actually concentrate on straight and level flying, which after all, if you're riding in a passenger in an airliner, that's kind of the sort of flying you enjoy the most as a passenger. So for straight and level flying, any good physics lecture has to begin with a free body diagram. And so here it is. So here's a free body diagram for an airplane in a level flight. And there's 4 forces acting. Of course, there's a force of gravity, the one that we always have to deal with. There's this upward lift force, and that's actually provided by air flowing over the wings. And it's actually a reaction force to the force that the wings exert on the air. But there's also this backward drag force, and there's a forward thrust force. For an airplane with propellers, the thrust force is basically Newton's third law. The propellers are devices that push the air backward, and so the air responds by pushing the airplane forward. They're pushing forward on the propellers. If you have a good engineer working on the airplane, the propellers are attached to the airplane. And so if that doesn't happen, I would advise get a better engineer to actually work on the airplane for you. So these are the 4 forces, and weight is the one that we all know. But these 3 are all involved. They're all reaction forces. They all involve the parts of the airplane pushing on the air. And lift and drag are actually the ones I'm going to talk about the most. But when we're in level flight, the sum of these forces must be 0, so the upward lift force must balance the gravitational force, and the forward thrust must balance the force of drag pushing aftward. Where does lift come from? If you look at detailed explanations of lift, you'll see all kinds of discussions that involve Bernoulli's equation, things that involve the Navier-Stokes equation, and it gets really complicated. But fundamentally, the simplest way to think about lift is it's Newton's third law of motion. And the third law of motion says if A pushes on B, B pushes back on A with exactly the same amount of force in the opposite direction. And that fundamentally is what the wing does. The wing is simply a device that takes the air that's from the frame of reference of the wing. If you're sitting in the airplane, the air is rushing toward you, and all the wing does, it takes it and pushes it downward. So because the wing pushes down on the air responds by pushing up on the wing. And fundamentally, there's nothing more to it than that. That's all the physics there is, really, for the physics of flight. But there are a lot more details with that, of course. So here's actually a question for you. So read this one over. This is what I do in my classes, by the way. Read the question over, consult with your neighbor, and after I hear some discussion going after a little while, I'll interview you, and you can tell me what you think the answer is. Well, here's some really good discussions going on here, which is great. And actually, as I say, that's the way I teach my classes. Most of the time in my classes, the students are actually discussing physics with each other. And I'll do that with a class of 300 students, so it's a pretty exciting place to be. And this is a pretty exciting place to be because I heard all these great discussions going on. So for instance, what did you think was the correct answer here?
I thought that since all the air had the same speed before hitting the wing, and when the wing pushes the air upwards, the total speed is greater because it has both x-axis speed and y-axis speed.
Okay.
So when it follows the wing, it has greater speed.
Okay, so you think the answer you're going for is A?
A or C, I don't know.
A or C, okay. Right. Well, and what did you guys think, actually?
We think C, actually.
Yeah, so you think C, and actually, if you ask most people, they'll say C. In fact, I've actually seen in documents for pilots from the United States Federal Aviation Administration, they actually give you answer C. And if you gave answer C, you have tremendous faith. In fact, you have faith that oxygen is a very intelligent molecule. Because think what you're thinking. You're saying these two bits of, think of two oxygen molecules. They get to the leading edge of the wing at the same time, and they say, okay, let's actually shake hands, let's agree that when we get to the back end of the wing, we're going to meet up. And so that's asking a lot for some oxygen molecules. And that's why the correct answer is, in fact, as you guys suggested, the correct answer is actually A. The air that flows over the top of the wing actually goes much faster than you might be led to believe. Some people think that because the top of the wing is curved, that the air has to travel a greater distance to meet up at the trailing edge, and that's why it goes faster. In fact, the real speed is much faster than that simple model would lead you to believe. In fact, here's a simulation from our Swedish friends over at Saab, actually looking at the airflow around a wing. These represent different particles of air that are about to encounter the wing, and you'll notice, so these are all at the same time, these are all at the same time, these are at the same time, and so on. And you can see the ones over the top of the wing are going much faster than the ones over the bottom. And as a consequence of going much faster, if you think about Bernoulli's principle, higher speed corresponds to lower pressure, and so that gives you substantially lower pressure on the top. And when I show this slide, in the States, people just say, what is that funny language? For you guys, you know what funny language is, but I do have to apologize, of course. But the best I could do. So air definitely goes faster over the top, and really only the air heels up quite some distance behind the wing. And we'll actually talk later on about what happens some distance behind the wing. So now we have this picture of what's actually happening with the air. It's going really fast over the top and getting deflected downward because of the manner in which the air flows. It turns out a big part of getting the wing to push the air downward is, in fact, the wing shape. So let's talk a bit about the wing shape. In fact, here's a natural wing. This is what you find on a flying squirrel. And you'll actually find these across northern Europe as well as in the United States. These guys don't really fly. They just sort of glide in a controlled fashion. And this is a species of squirrel that will climb up one tree, and instead of having to walk down to the ground to go to the next tree, it says, that's too hard. Let's just fly from one tree to the next. And so he has this natural wing, and you'll notice we say it's cambered. So it's curved down at the front and curved, so from the side it'll have a curvature like this. And that turns out to be a natural form that as the air follows the curvature of that wing, it'll naturally get pushed downward, and that produces a lifting force that enables this guy to glide. And you'll find that same structure on some of the very earliest airplane wings. This is a vintage 1917 American airplane, and there you can see the wings are curved very much like that membrane on a flying squirrel. And you notice also it's very thin. That's why the earliest airplanes were biplanes, one with two wings, because they thought the wings had to be very thin in order to be efficient, like the wing of a bird or like the wing of a flying squirrel, and they didn't know how to make a wing that was both thin and strong. But one thing they did know at the beginning of the 20th century was how to build bridges. And so it's exactly bridge building technology with these two spans here with struts between them that are under compression, and wires connecting them that are under tension, and that turned out to be quite a stable structure. It was actually only during the First World War, actually from research in Germany, that they discovered that no, a thick wing can actually be just as efficient, and that led to the transition from two-winged airplanes to the single or monoplane airplanes that we have today, where you can have the wing thick enough to have enough internal structure that it will hold itself up without this kind of bracing. And no good physics lecture goes without a few equations, so I'll hit you with a couple equations here, but not very many. And so here's the main equation for lift. And it turns out the amount of lift produced by a wing you can write as a product of three factors. One is it depends on the size of the wing. So if you imagine looking down on the wing from above, you'll see the wing area S, and we use the letter S because S shows up nowhere in the word area, so it's a natural choice of symbol. Say it just as natural as P for momentum. Makes about as much sense, frankly. And so the bigger the wing is, the more lift you're going to produce. As you might imagine, the heavier an airplane, needs more lift to hold it up against gravity. That's why you find much larger wings on large airliners compared to small airplanes. And the same is true for large birds compared to small birds. It also depends on the dynamic pressure. And that's the pressure you feel as you're running along or you're skiing at high speed or bicycling at high speed. That's the pressure you feel on your face. Mathematically, the dynamic pressure, if you want, it's 1/2 rho v squared, that factor that shows up in the Bernoulli equation, and which depends on the density of the air and the airspeed. So the greater the air density, today the air is relatively dense because the air temperature is low, so the air density is high, and the faster you go, the more dynamic pressure you're going to get. Also, any good physics equation has to have a fudge factor. There has to be a factor inside that absorbs everything that's too complicated to write down in a simple equation, and that is what we call the lift coefficient. That depends on the way the wing is shaped and also depends on something called the angle of attack. So what's that all about? So angle of attack sounds very military, but it applies to both military airplanes and civilian airplanes and to birds as well. It's the angle between the relative wind and the chord line. What the relative wind is, if you're sitting in the airplane, the direction of the relative wind, that's the way the wind is blowing over you. So if you're in straight and level flight, that direction is horizontal. You'd see the wind coming toward you going horizontally. And the chord line is an imaginary line from the leading edge of the wing to the trailing edge of the wing. The wing may be curved, but you think of this as just a straight line from the leading edge to the trailing edge. So the angle between those is called the angle of attack. So if the wing is biting into the air at a steeper angle, that's a large angle of attack. If the wing is relatively a small angle, that's a small angle of attack. So how does the lift coefficient depend on that? Well, generally speaking, the more lift to get more lift, you want to increase the angle of attack. At a low angle of attack, you can see in this illustration, the air gets pushed downward, but it doesn't get pushed down very hard. But if I increase the angle, the air following the curvature of the wing will be pushed down by a steeper angle. You may be going at the same speed, so the dynamic pressure is the same. You haven't changed the wing area, but because you've increased the lift coefficient, you've now by increasing the angle of attack, you've now increased the amount of lift. So generally speaking, all else being the same, if you raise the nose a little bit as you're flying, you can get more lift out of the wing. If you're flying slowly, you need to increase the lift coefficient. The reason is if you're flying slowly, as you might be when you're coming into land, at those slow speeds, you want to be going slowly so you can get stopped in a relatively short distance. You don't want to have to use 10 kilometers to stop the airplane because runways don't come that long. So you need to be going relatively slowly as you're flying along. That means the dynamic pressure is decreased. Remember, the dynamic pressure Q is less the slower you're going. So at slow speeds, Q is less, so to make up for that, to keep yourself flying, you still need lift because Q is smaller. You actually have to increase one or the other factor. And in this airplanes, we're actually increasing both. You notice the airplane is actually going downward a bit, but the nose is actually pointed above the horizontal. You may have noticed that on airline flights, you're maybe coming into land, but the nose of the airplane is actually tilted up a bit. So the angle of attack is between the direction that you're going, that's the direction of the relative wind, and the chord line of the wing, so that angle is pretty big. So that increases the lift coefficient. Also, the flaps at the trailing edge of the wing, those are down. And that does two things. One is it increases the overall curvature of the wings, which means the wings are now more effective at pushing air downward. Secondly, the flaps actually come back from the wings a bit, and that increases the wing area. So that does two things. It increases the lift coefficient, and it also increases the wing area. And by increasing those things, you can therefore fly at a slower speed where you have a decreased dynamic pressure. Is this a modern innovation? Well, not really. It's been around for millions of years. Because birds do exactly the same thing. This is a bird of prey, and what is this bird doing? It's hungry. It's looking for lunch. So it's found a likely spot, and so it's circling over that spot. And so it wants to remain going fairly slowly so it can stay over the same spot to find something attractive to eat on the ground. So to fly slowly, what is it doing? It's increased the curvature of the wing by putting the tail out. That's why putting down the flaps. Exactly the same thing. It's increased the overall curvature. By deploying those, you can almost feel how he's straining to stretch out his wings. He's increased his wing area. So he's increased the wing area, and he's also flying at a high angle of attack. All those things are increasing the lift coefficient, C sub L. And so he's at a low dynamic pressure because he's traveling slowly, but by increasing the lift coefficient and by increasing the wing area, that's just what it takes to enable slow flight. So it's exactly the same thing that you see with an airliner coming into land, where they have the flaps down, increasing the wing area and increasing the wing curvature, so that both the factors C sub L and S are increased to correspond for that decreased dynamic pressure Q. So as I said, lots of analogies between airplanes on the one hand and birds on the other. To see more about this stuff, the ideal thing to do is say, let's go for an airplane flight. So if I had a little more advanced planning for this talk, I would have arranged a sufficiently large airplane to take everybody. But so, well, let's do something almost as good. Let's go fly in an F-16. So one way to do that, of course, is to talk to our friends at the Royal Norwegian Air Force and say, I have some friends who want to go for a ride. Can we make that happen? And so he could just wander over to Erland and say, can I get a ride in one of these airplanes? You must have, a bunch of times you fly around with somebody not sitting in the back seat, so can I take my friends along? And they might not respond in a positive way. But nonetheless, we can imagine doing that. So imagine we're over there, and we're holding short of the runway, ready to take off, and you'll notice one thing you find on any of these jets is a large display in front of the pilot, and that's called the heads-up display. And that heads-up display is actually arranged so that the pilot doesn't have to look down at the instrument panel to see what's going on. The pilot instead can look straight ahead while flying the airplane and see the key information projected up there. So in particular, on this heads-up display, so-called because you can keep your head up, you don't have to look down to see the key information you need, we're actually going to use the heads-up display. We're going to do an experiment. And the experiment we're going to do is we're going to take an F-16, and we're going to bring the power back to idle. So the airplane is going to want to slow down, and we're going to tell the pilot, okay, the power is back, your airplane's going to be slowing down, but let's maintain the same altitude. What will it take to do that? So based on what we said, as we slow down, the dynamic pressure, Q, is going to decrease. So we're going to have to compensate by increasing the lift coefficient, C sub L. And to increase that lift coefficient, I said that that should increase with an increasing angle of attack. So let's see whether that's true or not. So we're going to look through the heads-up display as we do this. And so here's what we're going to see on the display. So in the video I'm going to show you, you'll see both the heads-up display the pilot sees, and we're also going to see the airplane as viewed from the side to see the way it looks as seen from outside. So we'll get both inside the cockpit view and outside the airplane view. The key numbers to look at over on the left-hand side, you'll see the airspeed calibrated in knots, which is a funny unit, but it's a little bit less than 2 kilometers an hour. Over on the right is the altitude in thousands of feet. I apologize for English units. Nothing I can do about that. We're also going to have our heading. Our pilot's going to try to keep the airplane going in a straight line, so that heading should remain constant. And the X will represent the direction of the longitudinal axis of the airplane. So basically, that's showing you where the nose of the airplane is pointed. Whereas the round circle is going to show you the direction that the airplane is going. The angle between those two directions, that's the angle of attack. Basically, it's the angle between the way the airplane is flying, which should be horizontal, and the way the nose is tilted up. The angle between those is essentially the angle of attack, the angle at which the wing is biting into the air. So let's see how that behaves. And in particular, I want you to look at the relationship between the angle of attack on the one hand and the airspeed in the other. As the airplane slows down, we're going to find we're going to have to increase the angle of attack. We're getting less air per second flying over the airplane. And so to compensate for that, we have to take the air we encounter and push it down harder with that greater angle of attack. So let's see if that's actually what happens here.
What must a pilot do to maintain level flight when decelerating with idle power? Determine the relationship between angle of attack and true airspeed for this decelerating F-16 in idle power and in level flight.
Gale is 3 degrees at the outside.
set true airspeed now 390. 3 degrees holding on the AOA. Coming down to 375 mark, 3.5 degrees on AOA now.
AOA is angle of attack.
Coming up on 350. Mark 350, AOA at 4.5. Disregard 3.5. Slowing to 325, ready. Mark 325, AOA is 4.2. Coming up on 300. Mark 300, AOA at 5.5. Coming up on 275. Mark 275, AOA at 6.5. Altitude lost about 50 feet so far. Coming up on 250. Ready. Mark 250, AOA at 8. Coming up on 225. Mark 225, 9.8 or so on the AOA. Bringing the nose up, airspeed's tuning quickly now. Coming up on 200. Mark 200, 11, disregard 12 on the pitch. Coming up on 175 mark, 175, 16 on the pitch. Holding 16. Coming up on about 150 mark.
So two things to notice there. One, you notice as the airplane slows down, look how high we have to pitch the nose. It really takes a large angle of attack as the airspeed comes up. You also notice the warning voice that came on is a female voice. And the reason they do that, they find with the predominantly male fighter pilots, if you give them a male voice, they ignore it completely. If it's a female voice, there's a chance they might pay a little bit of attention. You know, so in this case, he said, yeah, whatever. Okay. So what was that warning all about? Well, let's see. So here's kind of a graph that shows the behavior of the lift coefficient versus the angle of attack. And as we went slower, again, the dynamic pressure was decreasing. We're hitting less air pressure per second. And so we need to make the wing more efficient at producing lift. We need an increased lift coefficient. And so here you can see the lift coefficient increases as the angle of attack increases. And that corresponds to slower and slower airspeeds as you go along. But you notice there's a limit to everything. If the angle of attack gets too great, all of a sudden the lift falls off precipitously. There's a huge drop in the lift. And that's actually what the warning was about. The warning was saying that your angle of attack is getting close to the point at which the lift is going to drop off. And that's a phenomenon called a stall. And so what happens in a stall is you get this sort of phenomenon. The airflow flowing over the top, which previously had been in fairly laminar flow, going over the top of the wing, the airflow becomes turbulent. And that turbulent airflow no longer is giving you that nice, well-behaved phenomenon where the air comes over the top and gets pushed downward. Instead, the air over the top says, forget it, I'm not interested anymore. I'm still getting lift because the air on the underside is getting pushed downward. The stuff on the top says, not happening, not going to do it. And so as a result, the lift goes away pretty dramatically when this happens. And it's not just airplanes that have this phenomenon. That'll also happen for birds. For instance, here's another bird of prey on a winter's day looking for something on the ground. And this guy's flying so slowly, he's actually at the verge of a stall on the top of the wings. And you can actually see the feathers on the top of the wing are being pulled upward by the turbulent airflow. There's really some dramatic stuff happening there. You can actually see that in this video. This is a video of a bird hovering over a spot at really low airspeed. And if you look at the top of the wing, you can see some of the feathers being deflected upward because of that turbulent airflow. And the same thing happens for airplanes. The difference there is, of course, very few airplanes have feathers on the top, so you can't see what's happening, but nonetheless, you do get that kind of turbulent flow happening. So here's a question for you. Suppose you're flying along in your airplane, the nose gets too high, and all of a sudden the airplane stalls. So then what happens is, because the lift goes away, the airplane will start to descend rapidly. What do you do? Perhaps I say, what's the second thing you do? I know for many people what the first thing they do is, but the second thing you do, many people would say, oh my gosh, I'm heading toward the ground. They'll take the controls and they'll pull back to try to lift the nose up. That just makes it worse, because then you've just increased the angle of attack even more. So you have to do something that's very counterintuitive when you first learn to do this. Because you're going down, you have to push the nose downward. And that reduces the angle of attack, so then you're just in a dive, and then you can recover from the dive, hopefully with enough altitude. When you're learning to land a small airplane, you actually have to learn how to stall, because to do a proper landing, you actually stall the airplane 2 centimeters off the ground. And so that, when the airplane touches, the lift is pretty much gone, and so when it's down, it's going to stay down. I do see, when you go out to watch people learning how to land, you see people sometimes making wonderful landings, but unfortunately they do it at, instead of at 2 centimeters, they do it at 20 meters. And there it's usually not pretty to watch. You also see people who say, this is going to be a perfect landing. It would be perfect if someone had just made the runway 20 meters lower. And so it's always entertaining on a Saturday to go out to a place where there's student pilots and sort of watch the landings happen. It's often said that a successful landing is one where you can use the airplane again. And some of them look like they're frankly more successful than others. Okay. So again, a stall is really a real phenomenon and something you need to deal with. As I mentioned, a stall is something you want to do in every landing, and that's not just for airplanes, that's also for birds. This bird is actually just about to land. And so what has he done? The moment before this, he actually, and you'll often see many types of birds do this, they swoop down low and then they come up and plop down on a branch in order to land. So that's what he's done. He's swooped downward, now he's come upward, and he's about to land on this branch. And look at the top of that wing. You'll notice these feathers are sticking outward. And that's because they're actually on the verge of a stall. Just like an airplane should stall just before landing, this bird's doing the same thing. In fact, you can see, here's the direction he's actually flying, here's the angle of his wings, and the angle between those two things, the angle of attack, you can see is quite a large angle. Because of that large angle, he's actually close to getting a stall, and you can see those feathers deployed upward. And like a good pilot, he has the landing gear down and in the locked position, so he's ready to make a good landing associated with this. Stalls are a good thing if you're coming into land, but if you're trying to fly slowly, you want to prevent stalls from happening. You'd like to fly as slowly as possible without actually stalling the airplane. So, or in this case, stalling the bird. So what can you do about that? Well, this bird actually has an interesting bit of technology to delay the onset of a stall. Again, bird of prey looking for something to eat on the ground, trying to fly as slowly as possible. So because he's flying slowly, the dynamic pressure is quite low, trying to maximize the wing area. The tails are stretched out, the wing is stretched as far as it can, and maximizing the lift coefficient by flying at a high angle of attack. But again, if that angle is too great, you can stall the wing, and then he just falls out of the sky. Sometimes you'll see birds of prey do that. They just kind of tumble off on one wing due to just this happening. But how can I fly even more slowly? Well, you'll notice, look at the very front of the wings. There's things that seem to be sticking out. If you think of the hand as being like a wing, it's like his thumbs. And that's actually a structure on birds called an alula. And what does that alula actually do? Well, as the air, wonderful name. And so think of air as it goes through the alula. It actually makes a little slot. So as the air goes through there, think about the equation of continuity. For an incompressible fluid, when it goes through a narrow slot like that, it has to speed up. And that faster air going over the top can actually more easily adhere to the upper surface of the wing. By giving that air more kinetic energy, it's more easily able to follow the curvature of the upper surface of the wing. And that means the air, instead of separating from the wing, actually remains in contact with it, and that delays the stall. And by the way, you can see those same structures on modern airplanes. There we don't call them alulas, we call them leading edge slats. The flaps come down to the back, as we talked about before, to increase the wing area and the curvature. You also get some curvature from the leading edge slats, but they do something else. If you look close up, you'll notice there's a gap. And in fact, what happens there is exactly like the alula. It causes air on the underside to go through that slot and has to speed up. As a result, that air gets energized, remains in contact with the upper surface of the wing, and makes it less likely that a stall is going to happen. So you can fly at a slower speed and therefore be able to land at a much slower speed as well. And they'll also use these on airliners for takeoff, because for takeoff as well, you want to take off in the shortest distance possible. So you want to be able to fly at a slow speed to get off the ground. And again, preventing a stall at takeoff is a good thing to do as well. The leading edge slot was actually invented just about a century ago, and it was only later on that they discovered that, oh wait, these things exist in nature as well. So it's a wonderful example where technology thought it was being innovative, but in fact evolution had come up with the idea a few million years earlier. It's quite fun. We've been talking about lift, but what about drag? What about things that slow an airplane down? And the drag actually comes in a couple forms. I should mention, by the way, drag is important for understanding what happens to an airplane that's gliding. If you shut the engines off so the thrust is zero, the airplane is going to come down. If you look at the free body diagram for that and analyze it, and this is something I have my students do on the first day of class actually when I teach physics, is notice here's a free body diagram. And so you can figure out what the glide angle is based on making these forces actually balance out. And if you do the analysis, you'll find actually the glide angle is the inverse cotangent. Yes, the cotangent is good for something. And there it is. And the inverse cotangent is good for something occasionally as well. It turns out the inverse cotangent of the lift to drag ratio. So the more drag you have, the steeper that angle is going to be and the steeper the descent. And here's actually that angle. So here's the angle at which you're descending below the horizontal as a function of the lift to drag ratio. The more drag you have, the smaller that ratio is going to be and the greater the glide angle. So for a more gentle descent, that says you actually want to minimize drag. So keeping drag minimum is actually useful for a variety of things. You might think I want to keep drag to a minimum so I can go fast, but it also helps you to be a better glider as well. And it turns out there's a couple kinds of drag. The one we're most familiar with is called parasite drag. And that's a combination of pressure drag. Pressure drag is what you feel pushing you backwards when you stick your hand out of a car window when you're going fast on the motorway. It's the pressure of the air pushing back on the flat of your hand. And there's also viscous effects, because air has some viscosity. That means that the air actually will adhere to the airplane. And so as you're going along, you're actually dragging some air with you. Viscous drag is why we have car washes. If you didn't have viscosity with air and your car was dirty, it says, that's fine, I'll just go drive at 100 kilometers an hour. That'll blow all the dirt off. And in fact, you know, you could drive on the motorway at 100 kilometers an hour, or looking at this crowd, much faster. And you come back, the car's even dirtier. And it's because of viscosity, because the air right next to the car is not moving relative to the car. In fact, there, all that dirt just piles up instead. And so that contributes as well to the drag force on any moving vehicle going through the air. But the other one, the one that's kind of surprising, is this thing called induced drag, or drag due to lift. So we'll talk about both of those. Parasite drag in general, again, you need a good equation for that one. And for an airplane, it's mostly determined by the wing. Most of the drag actually comes from the wing itself. Depends on the bigger the wing you have, the more drag you have. The faster you're going, the more drag you have, the more dynamic pressure. And again, there's a drag coefficient that's kind of determined by the shape of the wing. And again, depends also on the angle of attack. Parasite drag is something you can actually modulate. For instance, this albatross is following a ship that has fish on board, and it's kind of interested in the fish, as you might imagine. And to regulate his speed, he actually puts out his air brakes. And the air brake, by modulating those, he can actually control how much drag he has so he can keep up with the ship that he's trying to follow. So there, by changing the overall shape and the amount that he presents to the air, he can actually regulate the amount of drag he encounters. But there's also this induced drag. And that's the funny one that people don't normally think about, because it's something you only find associated with wings. And it's called drag due to lift. If you think of this picture I showed you before, what happens to air as it flows over a wing, two things happen to it. If you just think of rotating the vector from horizontal to below the horizontal, two things happen. One, it acquires a downward component, so the air gets pushed downward, but also because the magnitude of the air velocity stays the same, that means that the horizontal component has been decreased. In other words, the air has been pushed downward, but it's also been pushed forward. It has less horizontal velocity now. So because the air has been pushed forward, that means that by the wing, that means the air is actually pushing the wing backward. In other words, the wing is feeling a backward or drag force because of that deflection. Another way to think about what's happening there is think about what happens out at the tips of the wings. As we said, there's high pressure on the underside of the wing, lower pressure at the top. What does air want to do when it has a difference between high pressure and low pressure? It wants to go from high pressure to low pressure. It actually goes around the wingtips. The problem is when it gets there, the wing is gone because the wing was moving forward. So the air ends up going like this, and the air starts rotating. It acquires some rotational velocity. And so as seen from behind the airplane, you'll get this rotational effect associated with the wingtips. As seen from above, you actually get these two counter-rotating vortices that are coming off the wingtips. It takes energy to make the air do that. Where's the energy come from? It must have come from the wing. So if you're getting energy out of the wing, that means the wing is having to do work, which means negative work is being done on the wing. And what does that do? It slows it down. So that's another way to think about where induced drag comes from. And to show you those vortices, here's a little video. Here's a wing in a wind tunnel. And notice as I go to high angle of attack, you can really see that airflow from the underside to the upper side of the wing and producing a vortex behind the wing. And we can actually visualize that. If we take this airplane and fly it past the tower with smoke, you can really see that vortex showing up associated with the wingtip. Also in this airplane, we have smoke coming off the wings. You can see it kind of twirling around either wingtip, producing these very strong vortices. That's the reason why, if you're at a big airport and your airliner is waiting to take off, somebody else takes off in front of you, you wait a couple minutes. And what you're waiting for is for the vortices from the airliner in front of you to dissipate. Because those vortices can be very strong. I've heard of small airliners being flipped over by the vortex from something like a Boeing 777. So that's why you wait a few minutes for those vortices to actually dissipate from the airliner in front of you. Here's another way to visualize those vortices. Here's actually an aerobatic team flying through some of their own smoke. And you really see those vortices being produced downstream and also coming off the wingtips themselves. Here's another great picture of an airliner that's descending through a cloud. And you can see those two counter-rotating vortices, one off of the left wingtip, the other one off of the right wingtip. So you're really seeing that effect of these wingtip vortices, and that has a lot to do with producing the induced drag. In fact, if you look at the whole picture of the way that air flows around the airplane, here's actually a picture. Imagine this not from the frame of reference of the airplane, where we think of the air as flowing over the air, over the wing, but instead imagine this from the frame of reference of the air itself. So as the airplane goes past it, what you actually see is there's a circulation of the air around the wing, these vortices trailing aft, and actually some distance behind that to conserve angular momentum, because you've given some angular momentum this way over here. You have to have the opposite sense of angular momentum back here. So it's actually like this big horseshoe that connects around behind the tail of the airplane. And there's a net downward flow through the middle of that. So the wing has this vortex actually attached to it, and that's what pushes the air downward. So it's rather more complicated than our simple picture of the way in which lift works. But it does take energy to make those vortices, and that corresponds to drag. Interestingly, as we saw from the video, at greater angle of attack, the vortices are stronger, so the induced drag is stronger. When do you have a high angle of attack? When you're flying slow. So in other words, this kind of drag is more important when you're flying slowly. And you can see that in this picture here, or for this equation. Here the induced drag, this drag due to lift, is inversely proportional to the dynamic pressure. Dynamic pressure is more important the faster you go. So at slower speed, Q is small, and therefore your induced drag is going to be big. So this is one that's actually more important the slower you go. You also notice it depends on the wingspan, the distance from one wingtip to the other one. And the longer the wingspan, the less induced drag you have. That kind of makes sense. We saw this happens because these vortices happen out at the wingtips. If B was infinite, if you had an infinitely long wing, there's no wingtips. And you can see if B is infinite, this goes to 0. So one way to eliminate induced drag is use an infinitely long wing. But of course, the problem with an infinitely long wing, it takes a long time to build. And you need an infinitely large runway to taxi around on. So it has some disadvantages. So here are these two types of drag. Parasite drag, important when you're going fast. Also more important in dense air, because that'll also increase the dynamic pressure. And it's also important if you have a really big wing. Whereas induced drag is going to be important when the wing's generating lots of lift. That'll happen both if a heavy airplane and also for one that's doing a tight turn. We're using the lift to make the airplane turn. It's important when you're going more slowly, so Q is small. It's important in thin air, because in thin air that also gives you less dynamic pressure, so you have a smaller factor Q in the denominator. And it's also important when you have a short wing. So all these factors play a role in these different types of drag. Since parasite drag increases as you go faster, and induced drag increases as you go slower, that says the total drag has an interesting shape. It's a curve that's high at high speeds, high at low speeds, and the curve kind of ends where you get to the stall. But there's a speed at which you get minimum amount of drag. And that's an important speed. That's where, to make the airplane fly, it takes the minimum amount of thrust. Which means if you have more thrust than that, you can use it to make the airplane climb. So that's actually the speed of minimum drag. That's actually the speed you fly at to get the best climb rate. It's also the speed, since we saw minimum drag gives you the best glide angle, that's also the speed that if the engine stops, and you want to be able to glide a long distance to find a safe landing spot, that's the speed you want to assume. So that's the speed at which the airplane is most efficient. So what's the speed at which airplanes actually fly? That's actually up here. And the reason we do that is because what's the whole point of an airplane is to go fast. And so you go as fast as you can, consistent with how much money you want to spend for fuel and the engine and all that. But if you says, you know, I think we're kind of running low on fuel, maybe we should slow down to this speed. That'll actually help you to maximize the distance you can travel as a result. To minimize the induced drag, that's important if you're in an airplane that's flying slowly. So for instance, here's a World War II German observation plane designed to fly slowly. So what did it do? It had really long wings, really large wingspan. That minimizes the induced drag because this guy's flying so slowly, induced drag is important. Induced drag is important when you're flying slowly, so you need big wings to do that. Also notice it has these big flaps that they're able to expand to increase the lift coefficient to enable that to delay the stall so you can actually fly at really low airspeeds. But birds have been doing the same thing for millions of years. This kestrel, another bird of prey, really long wings. And why are that? Because he also likes to fly at low airspeeds where induced drag is important. So to do that, you maximize the wingspan. Also, you notice the wings are tapered. And tapering the wing, as it turns out, also decreases the induced drag. Remember, the induced drag is increased because of air flowing around the wingtip. If you make the wingtips very gradual, where the wing curve gradually goes away to nothing, that will also minimize the vortices. And so this guy evolved this millions of years ago precisely to minimize induced drag. And humans have used the same thing on the World War II Spitfire fighter. That also was designed with these sort of tapered wings precisely to minimize induced drag. You might say, wait a minute, why would you care for a fighter? Fighters are supposed to go fast. Well, yes, they are supposed to go fast, and at high speeds, induced drag is not important, but this airplane was also designed to fly high. And at high altitude, the air density is less, so the dynamic pressure is quite low, and at low dynamic pressure, induced drag becomes important, whether you're flying fast or not. And so that's why that actually gives you this very distinctive feature of these guys. as I said, increasing the wingspan is really useful. And one way you can increase the wingspan, one problem you have, of course, if the wing is too long, it's hard to fit it into the spaces available at an airport. Turns out you can do almost as good if you take the wing and you just take the ends and you bend them upward. And that effectively gives you that same increased wingspan. And that's why in a lot of airliners you'll see these winglets. And basically they have almost the same effect as just extending the wing, but there's structural advantages to not having the wing really be that long. But it gives you much the same effect. It tends to decrease the wingtip vortices, hence decrease the amount of induced drag. Recently, several airliners have added these to the wingtips. It increases the fuel efficiency by about 3%. You might think, well, that's not that much. But if you look at the way airline economics works, 3% savings makes the difference between whether the airline stays in business or doesn't stay in business. So they like to stay in business, so making those changes has actually been very helpful for them. Is that a new innovation? Not really. These have been around for millions of years, and in fact, this Condor, again, he's designed to minimize induced drag. First of all, got a really big wing because he's a heavy bird, so he needs a big wing to produce lots of lift, but also a really long wingspan, different distance from one to the other. And notice the way the feathers are arranged out there. The feathers are kind of splayed out like this. That actually tends to minimize the production of wingtip vortices. In other words, it's designed to minimize induced drag so that this guy can fly along at a low airspeed, not need to flap his wings very often. As you can imagine, to flap wings that big takes a lot of effort. He'd like to do it as infrequently as possible. And so to make that happen, he makes sure the wings are stretched out as far as he can to minimize the induced drag, splay these things out like winglets on an airliner to minimize that. And so therefore he can fly around and look for something attractive to eat on the ground while this is happening. So lots of cool features you'll see similar to the way that birds fly and the way that airplanes fly. Of course, one thing that's dramatically different is that birds, of course, fly by flapping their wings. If you're in an airliner that flaps the wing, you might want to try a different airline. Totally different physics associated with that. I haven't said anything about flapping flight. Flapping flight's really quite amazing and much more complicated. Haven't said anything about turning flight, the amazing things that happen there, or the wild things that happen in an airplane that's actually in aerobatics. But as I said, straight and level flight, like I've been talking about, is the best paying form of flight. And so that's a good one to concentrate on. And if you understand that, then you can go on and actually study all the rest. So thank you all for your attention today, and I hope you enjoyed the talk.
With my mathematical knowledge, I'm going to try to give you, that's quite a lofty goal, but we'll see whether I manage to do that. I'll try to give you the talk that I should have had when I was a physics student.